So the next talk is also covered by Divya and Luisa, but this time they are not gonna talk. It's about yes, okay. It's about round optimal multi-party computation with Identifiable Abort, and Michele Ciampi is going to keep the talk.
Right, thanks a lot for the introduction. Yeah, that's a joint work with Divya Ravi, Lisa Ziniscalchi, and Andrew Bodner. Yeah, so this morning we learned that quite often we don't really want round optimality. So this is another talk about round optimality. And from Sophia, we also learned that broadcast is expensive. So we do round optimal MPC with broadcast in this talk. So in particular, the setting we are going to consider is the setting where there is dishonest majority. So in MPC, just as a brief reminder, we have this set of parties that want to learn the output of an input functionality, and in such a way that the dishonest parties will learn nothing aside the output of the function and their inputs. So in this talk, we will be focusing on the dishonest majority setting. And compared to the previous talk, here we will assume no setup at all. And the adversary here will be rushing. It means that before speaking and sending a message on the channel, the adversary will wait that other parties have sent the message. And all our constructions will rely on standard assumptions, in particular on trapdoor permutations. Everything will be proven in using black box simulation. So what do we know in this model? So when we have dishonest majority, we know that we cannot get fairness. So we cannot hope that either the honest party, all the parties get the output, or none of them gets the output. At least we cannot do that for some functionalities. There are simpler functionalities for which you can do that, but in general, that's not possible. We also know that even if we have broadcasts, in particular, we assume broadcasts where with simultaneous message channels, which means that like in each round, all the parties speak at the same time. Even if we have such a channel, we know that we need at least 4 rounds of communication. On the positive, we also know how to achieve this this bound, and there were a bunch of results in Crypto 2018 and TCC 2019, where we actually finally showed that we just need a special notion of oblivious transfer to construct an MPC protocol that is secure and that it's bound optimal. So, however, all these results are proven secure with unanimous abort. So, unanimous abort means that either all the honest parties get the output, or all the honest parties agree that there was an abort. With the identifiable abort instead, if the honest parties abort, then they will agree on the identity of a corrupted party. In this case, is the orange party. And the natural question is whether we need now more than 4 rounds. And in this work, we show that no, actually 4 rounds is everything we need. Then, yeah, relying on trapdoor permutations. So the natural way to go from a protocol that has unanimous abort to a protocol that satisfies identifiable abort, also in the past, the approach that has been used is the following. So let's say that we have a protocol that with unanimous abort that works over broadcast, right? Like we are focusing now on the messages only of this purple party. So what we could do is that we could attach the knowledge proof to all the messages of this protocol, okay? In such a way that given that if this zero knowledge is non-interactive, we know that every party can verify that the black message, let's say here, was computed correctly, okay? So the problem is that if you want to do that, you need setup, of course, unless you want to rely on random oracle. And if given that we don't want any setup and we don't want to rely on the random oracle, the idea would be to say, okay, fine. I mean, we know however, auto-construct zero knowledge in an interactive way without setup. So instead of attaching one zero knowledge proof, one non-interactive zero knowledge proof, we can attach just a 4-round zero knowledge protocol that we know how to extract from one-to-one one-way functions. So if now we focus just on the messages that are computed by one party, as I said, like each party in each round has an outgoing and an ingoing message. So now this party, for each of his outgoing messages, will perform an interactive zero knowledge proof where the statement is of the form like this black message for my MPC protocol, which is secured only with unanimous abort, is computed in a good way. And we do the same for all the messages of the MPC protocol. And so observe that this approach works only if the zero knowledge is publicly verifiable, in the sense that even if there is an external party that just observes the messages going over the broadcast channel for the zero knowledge, and even if this party is neither a prover nor a verifier, can still detect whether an abort in the zero knowledge was triggered by the prover or by the verifier. Okay, so it's like we need this notion of identifiable abort on the zero knowledge protocol. I'm abusing terminology here, but that should give the idea of what we need. So this property of public verifiability, we know how to get, but the problem is that I mean, this protocol is far from being optimal. Like here we have way more than 4 rounds. So one possible solution would be to not just run one zero knowledge proof for each of the messages, but to just run one big zero knowledge proof for all the messages of the MPC protocol. So to run a zero knowledge proof in parallel with the MPC protocol. So we get something like this, and then the zero knowledge will basically prove that all the messages, all the MPC messages have been computed correctly. Of course, like observe here that the statement of the zero knowledge proof will be fully specified in the last round. So you need a special form of zero knowledge and of soundness that we are referring as delayed input zero knowledge. And like the idea here is that if you apply such a trick, then what do you want? You want that during an execution of the protocol, at some point it might be that one honest party is not able to compute the messages of the MPC with unanimous abort protocol. So, but this party will just not stop, and he will continue performing the zero knowledge to prove that all the messages he has computed were computed in an honest way. Okay? And now the point is that given that the zero knowledge is publicly verifiable, like the only reason why a party would not be able to compute this zero knowledge proof is because the party cheated at some point in the MPC protocol. Okay, so so there are 2 issues with this approach. The first one is that the zero knowledge needs to be non-malleable. So I will not show how we deal with this problem. I will be focusing more on the other issue, which is composability. So actually, here we're saying that we are composing in parallel an MPC protocol and a zero knowledge protocol, but there is no reason whatsoever why this thing should be secure. And so the problem is that we actually don't know how to prove that this stuff is secure. And the reason is that when you want to prove the security of such a protocol, the thing you do is that you say, okay, fine, let's consider the real world experiment where we have honest parties that are computing the messages in the honest way. And then you consider a hybrid experiment where you replace the zero knowledge messages with messages performed by a zero knowledge simulator. Good. And then you say, well, these 2 hybrids must be distinguishable, otherwise I can contradict the zero knowledge property of this red special zero knowledge. And then in the final hybrid, you say, okay, good. Now I can just replace the MPC messages with the zero knowledge, sorry, with the simulator of this MPC protocol that exists by definition. And that's where this is the tricky part, right? Because here we want to say that now these two hybrids are indistinguishable due to the security of the MPC protocol. And this step in the reduction doesn't really work. And the reason why it doesn't work is the following. So when you wanted to do this reduction, you want to construct an adversary for this black MPC protocol, right? And this adversary now will interact against an MPC challenger that, as you all know, like he basically has two choices, right? Either the MPC challenger will compute the messages using the honest procedure, let's say, or using the simulator. And so, okay, so now we construct our adversary for this MPC protocol that internally will generate this big adversary for our protocol that should be secure with identifiable abort, right? And I mean, it's a pretty simple reduction. It's just that we construct an adversary that acts as a proxy for all between the challenger and the underlying adversary with respect to the MPC messages. And we just do that. Now the issue is that we are in the we have no setup. We are in the play model. So one way that the only way we know, let's say if we rely on polynomial time assumptions for a simulator to simulate is by doing rewind. So what happens here is that now that we are in a hybrid, we were in a hybrid where we were using the zero knowledge simulator. Now this zero knowledge simulator, we start doing some rewinds. But the problem is that now the adversary reacts on this rewind and changes the second message because he's receiving a second message for the zero knowledge proof. And the problem is that given that the adversary is rushing, the adversary will not send the third round of the zero knowledge unless he receives a new accepting message for the MPC. Okay? And the problem is that the challenger, like we cannot rewind the challenger. I mean, the reductions should be straight line. And we cannot ask now the challenger to reply to a new message that is like consistent with this new green message. And that's where the reduction fails.
So the MPC is also, you know, could be put into the, you know, whatever, the straight line simulator.
So, right, the thing is that here we assume no setup.
So then, but you need setup for the CK anyway.
No, this is a zero knowledge that we do in four rounds using just FLS. Exactly, there is no setup at all. So that's why, you know, yeah, the only thing you can do this unless you do other tricks that you might rely, you know, it's rewinding, and rewinding is devastating for composability, and that's one of the reasons why. Actually, that's a very good example. So yeah, the MPC challenger cannot be rewound. So what do? We need a stronger security notion of multi-party computation. And what we do is that we define a security notion that can be actually composed with other interactive primitive. So it's a notion of security that we call rewindable secure MPC, where basically we allow the adversary to send multiple second rounds and receive multiple third rounds. Okay. However, the adversary can do this for a fixed number of times, which is defined before the experiment starts. And let's call this parameter B. So we define this notion, but without abstraction, the definition is not that helpful. So one of the main contributions of this work is to show how to construct a protocol that satisfies this notion. So the main problem of the main reason, like why an MPC protocol is not secure, a general MPC protocol is not secure in this setting, is because allowing an adversary to rewind like from the third to the second round is actually kind of what also simulator does. So it's like it clearly creates a complication because it's like we are allowing the adversary to extract a trapdoor or an input, which is also what the simulator would do. So what we want to do is that we want to construct a compiler that takes any MPC protocol and turns it, you know, into a rewindable secure MPC protocol. And the overall idea is that the third round, which is what would leak something to the adversary, or at least it would leak something if we give multiple third rounds to the adversary, we want to encrypt these third rounds, okay, in such a way that nothing is disclosed or at least the adversary cannot do anything meaningful with these multiple third rounds because they're encrypted. The problem is that if we encrypt just encrypt the third rounds, then I mean the protocol cannot continue, because without third rounds, I cannot compute the fourth round. I mean, it's a problem. So the idea here is that the parties will just compute. For now, I'm focusing on the two-party case, but can be extended to the multi-party case. So let's say that we have just this purple party and the orange party here. So they will exchange the first two messages. And then the orange party will prepare a garbage circuit. This garbage circuit contains the transcript generated so far and the randomness of the orange party. And the input of the garbage circuit will be a third round that comes from this purple party. And basically, the garbage circuit will generate a valid fourth round on the behalf of the orange party. So it's like, instead of having the orange party generating this fourth round, it will be a garbage circuit that does that. Another thing is that to run a garbage circuit, we need to give the right labels to the purple party to evaluate the garbage circuit. And the way we do that is, of course, using oblivious transfer. And so now the point here is that if you want to input a third round to this garbage circuit, what do you need to do? Well, the purple party will act as a receiver, and by providing an encoding of the third round of this black MPC protocol. Okay, so instead, the orange party here will act as a sender using all the keys for this garbage circuit. And now the point is that by the security of the oblivious transfer protocol, we know that the orange party here should not learn anything about the input of the receiver. And the input of the receiver here is the third round of the MPC protocol, which is what we want to protect. So what we have here is that now the third round is encrypted. But at the same time, even if this third round is encrypted, the purple party will be able to receive in the last round of the protocol the garbage circuit from the orange party. And now she can evaluate the garbage circuit and get the fourth round of the protocol. Okay. And the same thing, it's done also by the other party. The protocol is completely symmetric. Okay. So, and then the parties will get the fourth round, and then they can evaluate the output of the function. Now, of course, the one question could be, okay, fine, but now you're running in parallel with an MPC protocol, an oblivious transfer protocol. How do they compose? So the point is that we know how to construct oblivious transfer protocols that are rewindable secure, so that are fine, even if an adversary can get multiple, can do some this mild form of resetting. And so this is basically more or less at a very high level how the protocol works. So of course, oblivious transfer is a two-party functionality. So our result works for multiple parties, and going to multiple parties requires still some non-trivial tricks, but at a very high level, that's how it works. So in summary, what we do here is that we propose this new definition of rewindable secure MPC, and the nice thing about this definition is that it could help composing like multiple interactive primitives together, which is something that in general does not work. And so we use this rewindable secure MPC as a gadget to construct multi-party computation protocol with unanimous abort. And like all our results, as I said, are based on Raptor permutations. But let's say we didn't put much effort in going like beyond Raptor permutations and using like, for example, semi-honest or semi-malicious oblivious transfer. But that's something that we think should be feasible. And yeah, that's the end of the talk. Thank you.
The beginning discussion of the rewindable. So on the definitional level, I think you probably have to take care of the fact that in the ideal model, you won't have to go through the process of giving the output didn't get
So
Can you give some context for the Zoom the question?
yeah. So so the thing is that so the thing good. So you don't need this relaxation here. The reason is that you would need this relaxation if when you do the rewind, you also allow the adversary at any rewind to get the output. If you do allow that, then you need to query the ideal functionality multiple times. I agree. But the point is that here we allow the adversary to rewind only between the third and the second round, let's say. So there is only one output that the simulator needs to force to the adversary. So it's one query to it's still one query to the ideal functionality.
So it's part of the notion.
Yes, it's part of the notion. Yeah, because in our notion we restricted, you know, we consider only this very specific type of rewinds. If you want a more general notion, yes. Yeah.
Any final question? Then let's start on the speaker of the session again.